Okay, let's get back into Turing machine business and all that jazz. Any questions on the first half? So no questions, that means literally 100% of people understood 100% of everything.
What's the best way of following along with like the note guide and you? I'm having a little bit of trouble figuring out where we're at.
So I have the notes literally in front of me, so I'm following my own notes. I have the boxes in there to have you print them out and then follow along as we're going along. But I let anyone do any way they want to follow along. But I'm following my notes pretty closely to what is listed there. I might not do exactly what's there. Not like I'm not looking at this and reading what's off there, but the examples are the same. The order of theorems is the same. That kind of thing. Yeah.
What do you mean by deciders again?
So a decider is a machine that always halts. A language is decidable if some decider has that language. Okay? So decider means a machine, decidable means a language. Okay?
And how did you correlate that with the theorem of union intersection?
So I said that decidable languages are closed in a union, which means that if I look at L1 union L2, that language must be decidable, but must be decidable and decided by this decider. So this is a high-level description of a machine for the union.
Oh, so it's a third machine.
Yeah, it's a third machine. Yes.
So like for intersection, it would be similar.
Yeah, we're gonna get to that. But yeah, we're making a machine based off of the machines that we are guaranteed exist.
So this example is just for union?
Yeah, just for union, yeah. But intersection, I'm only gonna modify this very, only a small bit. Any other questions? Okay, for intersection, how would I change what we just did for union?
They both have to accept.
Right, they both have to accept. So what would I do here for this accept? Should it be accept there for the intersection? No, it should be a continue instead. What about this otherwise continue? What should the continue be in that sentence?
So reject.
Should reject. Because if one of them says no, can it be in the intersection? No, good. So now, if we get to this point, if D2 accepts W, should we say accept there? Yes, because the only way we could have gotten to that point is if the first machine said yes, and then now the second one also said yes. So it means it's in the intersection. What about this reject at the end? That should also be the same because the second machine said no. And so it therefore can't be in the intersection either. Cool, we just got, and the runtime is the same because it's the runtime of the first one plus the runtime of the second, which is finite. And so therefore, L1 intersect L2 is also decidable. Okay? Any questions on that? Okay. Let's go on to concatenation. So remember, if we have two languages, A, B, it's I take any string out of A I like, any string out of B that I like, put them together via concatenation, throw it in the language. And so it's just the concatenated strings of A with capital B. So let's see. I'm going to be giving you a string, and I want you to tell me whether it's the concatenation of something in L1 with something in L2. Okay? Do I give you a delimiter as to where that split is? No, I don't give you a delimiter. Well, that sucks. What do we do? Well, maybe we can think of an idea. Let's look at a possible input. Let's say that's the input. Well, let's see. The split could be here, right? It could be there. It could be here. It could be here. It could be even over here on the left side. What is, if I have it be at this left point, what is the string on the left? The empty string, right? So that'd be the empty string over there. Oh, wait a second. How many possible splits are there? Not quite n, a little more. N plus one, right? If I have a single character, how many splits are there? 2. Namely this one and this one. Oh, if I have n characters, there are n plus 1 splits. Well, let's say that we do have a split. Let's say it looks like that. Could I check whether the first part of it is in the first language and the second part is in the second language in a finite amount of time? Yeah, why? They are deciders. Okay? So now we can actually get an algorithm out of this. So let's make one on input W again. Let's actually give the string the character names, just like the example we have. So for I equals, so now the indices are important. 1 to n plus 1, let's say. Run the first machine on, well, let's see. We're running from the beginning of the string to I or I minus 1. To I minus 1 in this case. Let's see, is that right? Yeah, that's right. Yeah, so the indices are, so this is actually a little more low level than it should be, but it's not quite to low level either. So this is like in the gray area. All right. But then we also run D2 on WI through WN. Yeah, that's right. So what if both of them say except? Then is it in the concatenation? Yeah, because we just found a split. Could there be other splits that work? Yeah, certainly. But only one of them is needed here. So if D1 and D2 accept, then we accept. Oh, no, not quite the end yet. Okay, well, we try this for the I equals 1, 2, 3, 4, up through the last value of I, and we decided none of them work. Now what? Could it be in the concatenation? No, we just tested every single possible split. Could it still be in the concatenation now? No, it can't be in the concatenation. So what do we say? We reject. Exactly. So we run through every iteration of this for loop, and every single time, either one or both machines said, no, it's not in my language, and then therefore it cannot possibly be in the concatenation. Yeah?
If I equals to 1, then step A runs from W1 to W0.
Right. So what is W1 to W0? It's the empty string. So it's to handle that first split. And the n plus 1 is to handle where Wi through Wn is the other split. Because in the last iteration, I will be n plus 1, so Wn plus 1 to Wn, that's the empty string on the right side. Any other questions? Okay. Now for a fun one. So I'm given a single decider for L1. Let's say the decider is D1. So we only have one to work with here. What does star mean, for those who remember? Yeah, just pick some positive non-negative integer number of times from L1, concatenate all of those strings together, and then put that in the star. So it's just repeated concatenation for some point. Okay, well, let's see. How can I do the star? Do we know how many splits there are? Well, let's see. Could it be infinite? Well, it could be, but what if we had a whole bunch of empty strings and then a character, then a whole bunch of empties, and then carried on? That I could do that as many times as I like, but are those actually needed? No. I only need actually one in between, because all of those will just collapse to 1. Actually, they collapse to 0, but I need to be able to handle that where there's 1. Because if it says yes on 1, is it going to say yes to every single version of the empty string? Yeah, it'll say the exact same answer to each one of these. So it's a finite number. We can work out the actual details, but is that needed in a high-level algorithm? No. So this one's actually even easier in some sense. So look at all possible decompositions of W and run D1 on each piece. If any decomposition has D1 except all pieces, what should we say? Except, because we just found a way of partitioning the string into pieces where D1 says yes on every single one, which means it's in the star of L1. So then we must accept. Then at the end, if we've tried every possible one and none of them had worked, so if none work, we reject. Because there's no possible way it could be in the star. Okay? Yeah.
Recombine means split into single digit, or like you're talking single digit?
Yeah, so it could be a single character or 2 characters, or so it's any possible way to partition the string into pieces. So it could be 1 piece into 2 pieces, into 3 pieces, 4 pieces, 5 pieces, 6 pieces. How many pieces could there be? Very close. N plus 1 pieces because of the empty string. So in fact, there are going to be precisely I'm sure we could work it out. It's escaping me at the moment, but it's at most n plus 1 pieces. So that's a finite number. And so the total of them must also be a finite number. So remember, the details are not needed in a high-level algorithm here. As long as we know it's a finite number, therefore this must run in a finite amount of time, which is all we need. Any questions on that? Yeah.
So it's saying split it up and D1 works on each one of the parts?
Yeah. So like if we have the string being this, and we partitioned it into these pieces, then I run D1 on each of the red pieces. Yeah. So I first will test the entire string because that'll just be looking at the looking into L1 exactly one time. Then I look into all possible ways of looking into L1 twice, then 3 times, 4 times, 5 times, and then all the way up to n+1. Any other questions? Okay, one more for decidable. So what about L1 bar? Yeah, it's the complement. So what is complement again? Yeah, everything in sigma star, but not in L1. So it's another way of saying sigma star without L1. You can do set minus L1 also. Let's see. If let's say D1 says yes on a string here, what should it do for L1 bar? It should a decider for it should say reject. What if D1 said no on a string in L1? For our decider, should it say no on L1 bar? It should say accept. So, in fact, this is the easiest one of all. So run D1 on W and output, which means say or return, output the opposite. Opposite. I think I spelled that right. Yeah. I can't even spell opposite. That's quite sad. But does this run in a finite amount of time?
Yes.
Yeah, certainly, because D1 runs in a finite amount of time. So in fact, decidable languages are closed under a whole bunch of stuff. Union, intersection, concat, star, and complement, which is pretty cool. So if you take any language you want, let's pick a non-trivial one, like the, I don't know. Let's say the L1 here. You can show that that's decidable. All the strings that are not powers of 2 in length, you can decide that because it's just the complement of this language. And if you take, I don't know. If you take all the powers of 2 length number of zeros and the language of all zeros in length that is a multiple of 3, union those together, that's a decidable language too. So we can play with that all day long with any 2 decidable languages that we want. Union, intersect, concatenation, star, and complement, we can play with those all we want. But are there any questions about why those are true? The more important thing from the theorems that we're proving is not the statement itself, which could be interesting, but the technique that went behind them. That's much more important. Are there any questions on those? Because the technique for proving for recognizable is going to be a little bit different. So the technique will actually be needed here. So another theorem which we'll prove is, so I'm just going to abbreviate recognizable to REC so I don't have to write it. Recognizable languages are closed under union, intersection, concat, and star. Is there one that I left out? Complement. It'll turn out that recognizable languages are not closed under complement, but we'll get there eventually. What does a recognizable language mean? Well, there's a recognizer for it. So let's do union. L1, L2 recognizable, and let's, instead of calling them D, let's call them R for recognizable. Recognizer. B recognizers for L1, L2. So now I'm giving you a string, and I want you to figure out whether it's in L1 union L2. What does a recognizer mean? What does that mean to be a recognizer? It has to halt on what strings? The ones that are in the language, right? So if I happen to give you a string in L1, if I feed that string to R1, will it halt? Yes, because it's a recognizer. If I feed you a string in L1, R1 must say accept, which means it runs in a finite amount of time. If I give you a string not in L1, must R1 halt? No, it doesn't have to halt. There's nothing in the definition that says it must halt. And in fact, many times it might not. Okay? Same thing with R2 and L2. So we'll have to think a little bit carefully about that. Okay, so let's see. Let's try the same strategy that we had before. So I'm just letting you know, this strategy will not work. So I'm full of bad ideas. I'm giving you bad ideas. So don't follow this idea. So our idea before was to run R1 on W, and then we did some stuff after. Anyone see anything wrong? Do I know W is in the language of R1? No idea. May R1 run forever? Sadly. What if I fed R2 instead? Same thing. Well, this sucks again. What do you think we can do? Ooh, what about in parallel? Well, let's see. If I run them in parallel, let's just say, for instance, that it happens to run forever. I run both machines at the same time, whatever that means. If I run them at the same time and it runs forever, could it be in the union? No. Why not? Because if it's in the union, one of the two must accept, right? Can accepting a string take forever? No. So if running them in parallel runs forever, neither machine accepts them. Which means it's not in the language, but I don't care about the strings not in the union. Well, the only other case is one of them stops, but that must mean it's in the union. Oh, so let's try them in parallel. So better idea. Let's try doing these in parallel. Well, what does run in parallel mean? Well, let's see. Maybe what we can do is let's simulate R1 for one transition. And then we'll simulate R2 for one transition. And then what if one of them accepts at that point? Is it in the union?
Yes.
Yeah. Well, then I say accept. What if both of them said no? How about run them for one more iteration? And then try again. If both of them said no, what do I do? Try again. Try again. Try again. Could that run forever? Yeah. But we're okay with that because that must mean it's not in the union. So in fact, we can say for I equals 0, 1, 2, etc. Let's see. Simulate R1 on W for one more iteration. Sorry, not iteration, transition. And then same thing, but for R2 for one more transition. C. If either accepts, should I accept? Yeah. So if either R1 or R2 accepts, we will say accept. Do I care if both of them say reject? No, I just run again, and again, and again, and again. Oh, wow. So do I actually halt on all strings in the union? If I give you a string in the union, will this stop? Yeah, because one of the machines will stop eventually, which means for one value of I here, it'll stop. Pretty interesting. So in fact, we can recognize the union here. I don't care about the strings not in the union, right? Questions?
I had a question.
Yeah.
I think I just figured it out.
Maybe tell me your question so everyone else can.
So I was a little confused on what you meant by having it run forever, but now I see with like one transition per.
Yeah, so if I knock this out right here, would my claim of union still hold true?
That one runs forever.
Right, R1 might run forever now. But now, because I insisted that it runs exactly one iteration, one transition, therefore that step A cannot possibly run forever because it only takes one transition. Yeah.
What's the transition?
So the R1, remember, is a Turing machine. So it's just we're in some state and the tape contents or something, and then we just simulate one more transition. So we save the contents of the tape and everything in the state onto the tape. So going low level here. Then we restore that information, run for one more iteration, and then save it again. Other questions? Yeah.
With that, if they both ran forever, wouldn't that mean that it's not necessarily finite time?
Well, so what does both run forever here mean?
If it just kept going, then
Right. So if I did infinitely many iterations of that, so that must mean R1 and R2 said reject over and over and over infinitely many times. Could it be in the union if both of them said reject forever? No, because if it accepts, it must do so within a finite amount of time. Due to the definition of accepting computation, which must be finite. Right, or reject, but we actually won't care about that here. Because I only need to care about the strings in the language here. Yeah.
So as long as one halts, you accept.
Yeah, at some point. Yeah, as long as one halts, then it's in the union, and then I say accept. But if either neither halt or both say reject at some point or something like that, then I'll never accept, but that's okay. Because I don't care about the strings not in the language. Yeah.
How do you decide the finite amount of time for our machine? What?
This might not run in a finite amount of time. Right? So this might run forever. But you need to show that it runs in a finite amount of time for the strings in the language, not for every string. But here, since it's in the union, one of the two machines must say yes at some point. So for some value of I, one of the machines must say yes if it actually is in the union, which means we will get to this except at the end at some point. Okay? Other questions? Yeah.
How does it save in between transitions?
So,
Everything that's doing.
good question. So we're talking about a high level here. We're not going to concern ourselves with low level here. But remember the configuration idea we talked about last time, where we saved the contents of the tape with that state character in the middle? So it's just writing that to the tape and then restoring it, looking at what thing we were looking at and looking at the transition function of the original machine, and then simulating it for one, then save it back. Yeah. We'll talk about multiple tape Turing machines in maybe today or next time. So we'll see. Oh, by the way, is there a class on Wednesday? No. So what I'm going to do is I'm going to do a video lecture and upload it probably tomorrow so that you can watch it and all that. But any questions on this? Yeah.
It doesn't have to be one transition.
Yeah, it doesn't have to be one, but you're never wrong doing just one here. I got to put some finite number down. So 0 is not good, but 1 is good. Yeah.
This is more of a general question about recognizers. If it doesn't have to halt on reject, then how do you know, like, what's the use of them? Because something could go for a very, very long time, but still end up stopping, but then you'd have to wait a very, very long time. Or,
Right.
like, you don't know how long you would have to wait in theory.
Because we'll eventually show that decidable and recognizable languages are not the same. So there needs to be, and we'll show some languages that are recognizable and not decidable. So there needs to be a distinction here. So if they were the same, then I would have proved that first, but they're not. So it's just a natural consequence of the definition and the fact that there are undecidable but recognizable languages. Other questions? Okay, what about intersection? We actually only need to change one word here for intersection. R1 and R2. But I mean, I guess either goes away. Then, and the S on the end of that. But it's really easy to change it, right? The correctness is almost exactly the same as for union, but here it's just intersection. If both of them say yes, then we say yes. So that's easy. What about for concatenation? So I'm only going to sketch these. So if we remember back to the concatenation from before, we broke into pieces the input, and we ran the machine on the first part and the other machine on the second part. And if both of them say yes, then we say yes. Can I do that for recognizers? No, why not? It could run forever. So what do we do here? What do you think we should do? Yeah, it's a similar idea. Just run all possible of those n+1 splits in parallel. So I'm just only going to sketch this. Run all n+1 splits of input in parallel. So by this we mean, of course, one transition for each at a time. If at any point both pieces are accepted, we accept. Both pieces of some split. Sorry for my atrocious handwriting. I'll try to fix. So it's just the exact same idea as for the concatenation for decidable, but we need to be careful in that we run them in parallel instead of running the entire machine at once, because recognizers might run forever. What about for star? Same idea? Yeah, so same as concat, but all possible decomps. So it's just like decidable for all possible decompositions, but now we're just going to run them in parallel in the same sense. Run one transition at a time until we either run forever or one of them says yes. So in fact, all of the recognizable languages are closed under union, intersection, concat, and star. Cool. Any questions on that? So why do you think it's not for, it won't work for complement.
So if you're trying to return the opposite, see if it rejects to return true.
Right. So that doesn't prove that it doesn't work, but it's a good intuition because we only have to halt on the strings that are in the language. We don't have to halt on the strings not in the language. So if we just flip the answer to be from accept to reject and from reject to accept, well, I might not halt on the ones that say reject. And so therefore, I might not be a recognizer for the complement. So in fact, we're going to prove something right here that characterizes when a language is decidable versus recognizable and its complement being recognizable, unless there are other questions. So this one's actually one of the more interesting theorems. So L is decidable, a language L is decidable, if and only if L is recognizable and L bar, its complement, is recognizable. If and only if, so a double-ended arrow. Yeah. Yeah, if you can't read my atrocious symbols, just tell me. Well, let's see. So what does this tell us? It tells us that if we can decide a language, then we can recognize the language and recognize the complement of that language. It also tells us that if we can recognize the language and recognize its complement, then we can actually decide the language. So there's both directions we need to prove. So let's do the easy direction first, which is if I have a decider for L, then I must have a recognizer for L and a recognizer for L bar. Is that true? Well, I mean, it's the theorem statement, so it must be true. But why is that true? If L is decidable, is L bar recognizable? Yeah, why is that true? It's just the definition, because we talked about that earlier. So I'll put def there. It's definitely the definition. Well, let's see. We got to get down here to L bar recognizable at some point. If L is decidable, is L bar decidable? Yeah, why is that true? We just showed that decidable languages are closed under complement. Good. So this is closure under complement. Nice. Oh, wait a second. What about this last one? For L bar decidable implies L bar recognizable? Is that true?
Yes.
Yeah, that's just the definition again, but just for L bar instead of L. So this is the definition as well. So in fact, if L is decidable, then that must mean that L is recognizable and its complement is also. Nice. What about the other direction? We haven't shown, and it's not true, that L recognizable implies L decidable. So we can't apply the same idea as we just did to, we can't just reverse the arrows or something. So we need to be a little bit more clever here. So what does the decider mean? What does a decidable language mean? Because it actually will help us here. It halts on all strings, right? What does a recognizer mean? Halts on all strings in the language. Wait, can a string belong to a language and its complement? The language's complement. Can it be in both? No. Wait a second. If I give you an arbitrary string, will one of the either recognizer say yes? One of them will, because can it be in neither the language nor its complement. No, it must be in exactly one of the two. So one of the recognizers must say yes. Okay? One of the recognizers will say yes. But we can't use that idea of run the recognizer for L on that input and then run the recognizer for L bar on W. Why can't we do that?
What else might
Can recognizers run forever? So what do we do? How about our parallel idea? Isn't parallel awesome? All right, well, let's see. We need to write a decider that always halts on all strings. So let's see. On input W, well, let's see. Let's just try our idea of running for one step repeatedly over and over. So let's do for I equals 0, 1, 2, etc. Run decider, oh sorry, there isn't a decider for it. Run recognizer for L on W for one step, more transition. And then same thing, but for L bar for one transition. So this is our parallel idea. Just run the recognizer for L for one more step, run the recognizer for L bar for another step also. But we have to be a little bit careful. So this one will seem kind of obvious, but you'll see why I'm asking it. What if the recognizer for L says, yes, it's in my language? What should the big machine that we're making say? The recognizer for L said yes. So is it in L? Yeah, it must be in L. So what should we say? We said it's in L. We want a decider for L. So we should say accept. So if L accepts, I should say, if the recognizer for L accepts, then we accept. But now we just need to think a little on this one. If the recognizer for L bar accepts, what should we say? Reject. Why?
Because it's a decider for L.
It's a decider for L bar. It said the string is in L bar, which means, but we're trying to decide L, so we should say no, it's not in L. So we should say reject. Seems like a good idea, right? It is, but it seems like a good idea. Is there a potential problem with this? Who spots an infinite loop? It looks like an infinite loop to me. 0, 1, 2. There's no upper limit on that. Can this run forever? Seems like it could. Why won't it?
One of the machines.
One of the machines will say yes at some point. It may take 1 trillion transitions, right? One of the machines, L or L bar, will say yes at some point. Oh, wait a second. If those machines take a finite amount of time to say yes, then we just figured out whether W is in L in a finite amount of time. So did we just make a decider? So we know this machine is a decider. Pretty cool. So let's just recap. For the first part, we just applied the definition and that result of closure into complement. And then for here, we just applied our idea of parallel, but we needed to be a little bit careful for the L bar case. But we were actually, because we're working with L and L bar, that we could actually decide the language because one of them will eventually say yes, which is pretty cool. Any questions on that? Yeah.
How do we know that it'll say yes?
Right. So can the input belong to L and L bar simultaneously? No, because it's the complement. It's all the other strings. Could it be in neither of them? No, because it's either in L or in all the other strings. Right? So it's in exactly one of them. So exactly one of those two machines will say yes at some point. Right? And so therefore, at some value number of iterations, one of the two machines will stop and say yes. Okay? Other questions? What do we got next? Ooh, fun stuff. Unless there are other questions. Okay. How much time? 8 minutes, plenty of time. So the next topic that we're going to talk about is, well, you may be a little annoyed at Turing machines. Well, everyone in this class is probably annoyed at Turing machines by now. That my computer can access memory in its cache or whatever in a random access way, right? It says go to address 8000 and it'll instantaneously go there. It's not instantaneous, but it doesn't have to do addressing one by one until it reaches there, right? So you may think, well, that's kind of annoying for Turing machines. It may do the same things as my computer, but it does it much slower. So, or maybe you may be a little annoyed that a Turing machine exactly moves one transition left and one transition right, but it can't stay still. It can't stay in the exact same cell. And so you may think, well, what if we altered the definition of Turing machine to have some variant of a Turing machine? Do we get other languages? Do we get maybe not as many languages? Or do we get the same number of languages that Turing machines normally decide or recognize? So what we will want to show here is, in fact, in any reasonable variant that you can come up with, in fact, we can show is equivalent to the standard model. So if we have a Turing machine, a normal Turing machine, we can convert it to whatever model we want and the other way around. So in fact, they're equivalent in computational power. They might not be as fast, or they might be faster, I don't know, but they can compute the same things, which is what a Turing machine variant is all about. So the example I have in the notes is what's called a stay put, TM, my term. And what we have here is, if we have a tape and we have the tape head pointed somewhere, then either the tape head can move left, move right, or not move at all. So it's allowed to stay in the exact same place and not move. Okay? Question. Can a stay put Turing machine simulate a normal Turing machine? Yeah. Does a stay put Turing machine have to stay still at some places? No, it doesn't have to. So it just does the left and right whenever the machine that it's simulating does the left and right. So that shows that stay put Turing machines are at least as powerful as the standard model. But now we need to show, can a normal Turing machine simulate a stay put Turing machine that may have stay put transitions in it, where it does stay in the same place? Can a normal Turing machine simulate a transition where you stay in the exact same place? Yeah, how would you do that? Ooh, can I go left then right? Maybe. Why may I not be able to? Because if I'm at the very left-hand end of the tape, if I try to move left, that's what's called hanging yourself in the literature. We're hanging ourselves by falling off the left-hand end of the tape. Not my term. So what's a safer option? Move right then left. So if a stay instruction on the transition, then move right, then left. I'm serious, that is the terminology. But yeah. So in fact, and what about if a stay-put Turing machine has a left transition? What does the normal Turing machine do? It does a left, and right, it'll do a right. So we're just simulating via the normal transitions of the Turing machine with this possibly more powerful variant. Cool. Any questions about that? So we're not going to have enough time to do this one, but I'd like for you to at least think about it. So this model is called a multi-tape Turing machine. So you may be annoyed that for a normal Turing machine, we have to move left and right possibly a long way on this one tape. But maybe if we had multiple tapes that we can use, then we can move right on one tape and then move left on another tape and then right on one tape, etc. And so it may be a lot quicker to be able to compute some. Yeah.
So does it matter if can you specify your inputs to these machines? Like when you say computationally the same, does that mean that all inputs for your regular Turing machine will work for you can create an instruction set, or a state machine that would work for that same input? Or
So the computational equivalence here means if a language is decided by a normal Turing machine, it's if and only if it's decided by one of these variants. So the class of languages for decidable is exactly the same, whether you use the normal model or the variant.
So it must be the same input, right? So it must be like
No, it's whatever input that you're given, you must have the same language. You must accept all of the same strings. No matter what strings you get, you must accept exactly the same ones.
right. But what I'm saying is like, say you could only move, you could accurately every given spot on the tape, because you can only move left by 2 and right by 2.
So then, well, what you would do in that case is for the normal Turing machine, if you can only move, you can't move 1, you have to move an even number, or only by 2. What you would do for the normal Turing machine is you would just ignore, you would duplicate every transition, and so therefore it would work.
But you can't go backwards, right? From this machine to a normal Turing machine.
What do you mean go backwards?
Like we can simulate this machine with a normal Turing machine. We can simulate a normal Turing machine with this Turing machine.
Actually, yeah, I think that's different. Yeah, we can talk after class about that. Any questions before I let you go in 4 seconds? Actually, no, I'm so sorry. It goes to 7:30, so we have 5 minutes. Sorry to let you down. But I want you to at least think about multi-tape Turing machines. So a multi-tape machine is we have some number of tapes, which we'll call K, at least one, where each of the tapes will have independent control of its tape head. So maybe, for instance, this transition will move right on this next transition. The first tape head will move right, the second one will move left, and maybe the third one moves right. Okay, so I have independent control here. So can a multi-tape machine simulate a normal single-tape machine? Yeah. What do you do? So the first tape, what do you do on the first tape? What the normal Turing machine did. What do you do on the other tapes? We can always just move right on those, right? Because I don't care what happens on the other tapes. Yeah.
The tapes all have the same input on them?
Good question. So the way that the multi-tape machines are going to work is the input is going to be only on the first tape, and all of the other tapes are blanked out. A good question. So, but of course, what we can do at a high level is we can copy the input onto the other tapes if desired, but we don't have to do that. But the way the model works is that it'll start off with the input on the first tape and everything else blank. So clearly a multi-tape machine can simulate a normal one just by ignoring what is called on the other tapes. Now it's the important question. Yeah, go ahead.
Can the tapes move at the same time?
They will move the same on the same transition. Yeah, so one transition applies, all K tape heads will do something. Okay, now the important question. Can a multi-tape machine, can a normal Turing machine simulate a multi-tape machine on a single tape? Seems a little difficult, right? Think about this language. Don't worry about whether they're the same or different as before. Could we use this idea? So I'll give you a high-level idea now, and I'll describe it in the video that I'll post tomorrow. What you do is, this will be the contents of tape 1, contents of tape 2. This is tape K. And then in a single transition, what we do is we have a dot on some character in each of the tapes, the corresponding tapes, that'll indicate where the tape head was on each of the tapes before. We scan right through this long input, this long tape, and then we simulate the transition, figure out what the transition is, and then carry it out. And then go all the way back, try again. Simulate another transition, go back, simulate, and that's it. Any questions before we break? I'll give you a minute early. I'm so generous. Reminder, there's no class on Wednesday, and we have office hours right after this. And no office hours Wednesday. No office hours Wednesday.